A sheet of aluminum foil, ordinary table salt, and a glass of water. Online videos promise this combination is the secret to endless free heat. The fascinating thing is that the underlying chemistry is not completely fabricated. There are 15 megajoules of energy packed into every single kilogram of aluminum, but it is trapped behind an oxide wall, measuring merely 5 nanometers in thickness. Shatter that wall, and you do not simply generate heat. You release hydrogen gas, which is highly combustible across almost its whole range of concentration. This is the exact point where a harmless household hack transforms into a legitimate hazard. While a piece of foil appears to be just plain, bare metal, its surface tells a completely different story. The moment raw aluminum meets the oxygen in our air, it builds a protective skin of aluminum oxide, or Al2O3. This barrier is exceptionally thin, ranging from 3 to 5 nanometers, making it roughly 20,000 times finer than a single strand of human hair. Still, this microscopic, invisible shield is the primary reason your kitchen foil does not suddenly heat up or start fizzing when exposed to moisture and salt. Think of this oxide film as a microscopic vault, perfectly isolating the reactive aluminum inside from water, acidic substances, and common salts. Surface chemist Dr. Santos refers to this phenomenon as a regenerating suit of armor. If you manage to scratch the surface of the foil, the oxygen in the air immediately reacts to heal the wound, reforming the oxide barrier in a matter of seconds and preventing any further chemical invasion. This protective layer is incredibly dense, lacking a defined crystalline structure, and virtually impenetrable by water molecules. Even at such a tiny scale, it acts as a perfect electrical insulator, trapping the electrons needed to spark a chemical reaction. This explains why soaking foil in tap water or even in a heavily salted kitchen bowl results in absolutely nothing. You will see no bubbles, feel no warmth, and generate no hydrogen gas. The only possible method to tap into the massive energy reserves of aluminum is to find a way through that armor. Out in the industrial world, chemical engineers rely on highly concentrated acids or powerful bases to melt this oxide away. Sometimes they use abrasive mechanics or specific metal ions to forcefully strip the barrier. But back in your kitchen, the sheer toughness of this oxide skin means that any trending video claiming to unlock instant heat using only grocery store salt and water is completely ignoring the fundamental roadblock. That microscopic layer is a vault crafted by nature, and it requires a very specific key. Until you can reliably breach that wall, the immense power contained inside the foil remains entirely out of reach for everyday household ingredients. Dr. Santos lays out a pristine, shiny sheet of aluminum on the table. He scatters ordinary table salt over the surface and pours on a bit of water. It is the exact setup you see in those viral clips, yet the actual outcome falls entirely flat. When sodium chloride, NaCl, mixes with water, it quickly dissolves, flooding the solution with chloride ions. In the corrosion industry, these specific ions are known troublemakers. They actively hunt for vulnerabilities in protective oxide films, often initiating what is known as pitting corrosion. While they are infamous for chewing through industrial metals, their impact on your standard kitchen foil is incredibly underwhelming. The foil's oxide shield stubbornly holds its ground. You might occasionally spot a handful of microscopic bubbles clinging to the cut edges or forming deep in the creases, suggesting a tiny localized failure in the armor. As Dr. Santos explains, these minor reactions almost always happen right at a physical scratch or a microscopic flaw, areas where the protective skin was compromised before the water even hit it. Furthermore, the salt in your pantry is rarely perfectly pure. It often carries trace amounts of alkaline compounds or anti-caking agents that can bump up the pH levels just enough to slightly aid in breaching the barrier. But even with those impurities, the overall chemical reaction is incredibly weak and wildly inconsistent. The overwhelming majority of the aluminum sheet does absolutely nothing, and the temperature of the water barely shifts. What those internet hacks conveniently edit out is this exact inconsistency. They gloss over the crucial requirements, like physically scraping the foil using chemical impurities or applying high heat, that actually make chloride-driven pitting possible. If you run this in a strict laboratory environment using pure sodium chloride and plain water, almost nothing happens unless that foil has been specially treated beforehand. Chloride ions might poke and prod at the oxide layer, but they simply cannot force the catastrophic structural collapse required to unleash meaningful heat or hydrogen gas. The internet rumor survives because it is built on a tiny fraction of chemical reality. Chloride ions do play a role in corrosion, but just as Dr. Santos shows us, table salt is simply the wrong key for a very heavily guarded lock. The actual breakthroughs require heavy-duty chemistry, not simple pantry shortcuts. Picture a glass beaker filled with a sodium hydroxide solution. When Dr. Santos drops in a fresh strip of clean aluminum, the reaction is immediate and violent. Within moments, the liquid is boiling with bubbles, and the thermometer rapidly climbs. It is loud, aggressive, and unmistakable, a far cry from the lazy fizz or mild warmth shown in those viral kitchen clips. In a controlled lab setting using a 5 molar sodium hydroxide bath heated to 60 degrees Celsius, measurements prove that aluminum can pump out 0.2 liters of hydrogen gas for every single gram of foil. The temperature spikes instantly, frequently jumping more than 10 degrees in a matter of minutes. But remember, this is not free energy. Every single joule of that heat is the direct result of oxidizing the aluminum. As the reaction burns on, the metal is visibly eaten away. The real secret weapon here is the powerful base. Those hydroxide ions do not just poke at the armor, they obliterate the oxide layer entirely, dissolving it into soluble aluminate and leaving the raw, vulnerable metal completely exposed to the water. This process generates a massive amount of heat, and scientists can dial it in precisely by tweaking the bath's temperature and concentration. However, the safety risks are severe. You are dealing with highly flammable hydrogen gas and a deeply caustic liquid that can cause severe chemical burns. This is serious material science, not a fun weekend trick. Adding copper to the mix takes things to a completely different level. If you coat the foil with a microscopic layer of copper, maybe by dipping it in a copper sulfate bath or pressing copper sheets right against the aluminum, the reaction kicks into overdrive. The copper acts as a galvanic catalyst. It supercharges the flow of electrons and completely destabilizes that oxide shield. In standard lab tests, alkaline solutions acting on copper-activated aluminum can unleash an astonishing 1.8 liters of hydrogen for every gram of metal, accompanied by a massive surge in heat. The results are highly measurable and consistently reproducible, completely blowing away anything plain salt could ever hope to achieve. This deliberate, aggressive chemical unlocking is the crucial step those viral videos leave out. And it is not just about the chemicals. The actual physical shape of the aluminum dictates how fast this reaction happens. Dr. Santos sets up a brilliant comparison, a perfectly flat sheet of foil pitted against a tightly crushed ball. Common sense suggests that crushing it up would help by creating a ton of sharp edges and tight spaces for the chemistry to work its magic. But the hard data on hydrogen output paints a completely opposite picture. In rigorous testing, foil that is gently folded or loosely stacked beats a tightly compacted ball every single time. It all comes down to basic surface access. When you crush foil into a tight sphere, a huge percentage of the metal is buried deep inside, totally blocked off from the liquid. The outside shell reacts, but the core remains perfectly preserved, trapped inside a cage of its own making. A rigorous study from 2016 proved exactly how much this matters. They found that foil folded into simple zigzag shapes pumped out roughly 30% more hydrogen than dense balls of the exact same weight, sitting in the exact same alkaline bath. That boost did not come from a chemical change, it was pure structural engineering. Smart folds and open layers maximize the exposed surface area, allowing the reactive liquid to constantly find fresh metal as the oxide melts away. A crushed ball just shields itself, killing both the speed and the final output of the reaction. As Dr. Santos notes, this is a textbook example of physical architecture directly throttling chemical velocity. The takeaway is simple. Even if you have the perfect chemical bath, your aluminum will only release its heat and hydrogen if the liquid can actually reach the metal. Viral hacks ignore this entirely, but in real science, geometry is everything. Aluminum undeniably contains a massive reserve of chemical power, precisely 15.1 megajoules per kilogram, verified by strict thermodynamic testing. However, that power is not magically conjured from nothing, and it is certainly not unlimited. In any legitimate scientific test, the heat and hydrogen gas are produced exclusively because the aluminum is actively being destroyed, atom by atom, via oxidation. Professional scientists view this entire reaction as a method for creating hydrogen fuel on demand, rather than some impossible perpetual heat generator. When scaled up to industrial pilot programs, a system using copper-boosted aluminum in an alkaline bath can crank out roughly 9 kilograms of hydrogen every single hour, running at an overall energy efficiency of 62%. While those statistics are incredible, they require tightly controlled, heavily engineered reactor tanks, not a glass jar on your kitchen counter. In fact, patent officials evaluating these so-called free energy submissions consistently point out that because the aluminum is physically eaten away, it is simply a fuel consumption process, not a miraculous energy breakthrough. The actual hurdle scientists face is safely containing this massive energy yield, and this is exactly where the danger truly spikes. Once hydrogen gas enters the equation, the threat level skyrockets. Its combustion window is incredibly wide, able to ignite anywhere between 4 and 75% concentration in normal air. That means even the tiniest leak acts as a severe ignition risk. Local fire marshals have even been forced to put out public safety warnings directly addressing these trending, unsupervised foil and salt science projects. Consider a recent incident at a high school where a student attempted to grind up aluminum foil into salt water for a class project. It started as a mild reaction, but as the invisible hydrogen gas accumulated in the room, a rogue spark from nearby lab equipment almost set off a massive flash fire. Thankfully, no one was hurt, but it was enough for the school to completely ban the experiment outright. Safety experts constantly reiterate that hydrogen gives no second chances. It disperses rapidly, you cannot see it, and it catches fire with almost zero warning. What starts as a harmless viral trick can violently cross into dangerous territory if that chemical reaction escapes your control. These online claims purposely skip over the harsh truth. Unlocking real heat from aluminum requires literal material destruction, and once that hydrogen forms, you are dealing with a severe safety hazard. There is simply no magic pantry ingredient that can bypass the laws of chemistry. Modern science is focused on harnessing this reaction for safe, controlled hydrogen generation, completely debunking the fantasy of free, endless warmth. The internet myth is an easy story to sell, but the physical reality commands absolute respect. Question the viral hacks, respect the chemistry, and always stay safe.